Okay, we're going to be doing lead code 1337, the k weakest rows in a matrix, and you're given an m by n matrix, binary matrix. By binary means contains ones or zeros, called mat, of ones representing soldiers and zeros representing civilians. The soldiers are positioned in front of the civilians. That is, all the ones will appear to the left of the zeros in each row. So this means there's some sort of order, right? So that means you can partition each row into sections, right? That's a hint for binary search. So a row I is weaker than a row J if one of the following is true. The number of soldiers in row I is less than the number of soldiers in row J, and both rows have the same number of soldiers, and I is less than J, right? So what that means, if they have the same number of soldiers, but I comes above J, in other words, the way we count the rows is, this is row 0, row 1, row 2, row 3, row 4. So for example, if you see this row and this row have the same number of soldiers, but this row is at row 0 and this is at row 3. So this is the stronger row, right? And then you're supposed to return the indices of the kth weakest rows in the matrix ordered from weakest to strongest. So they give us a k and we're supposed to return the k weakest rows, right? So that means that once you've sorted them in an array, right, maybe it will go beyond this, you'll return the first 3. If our k is 3, you'll return the first 3 in that row, in that sorted list. So what we're going to do, we'll use this matrix as an example, right? So we have here a matrix. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Oh crap! Hold on a second. Okay. Oh, this is really nifty. Oh, this is actually dope. Okay, 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? So this is 1, 1, 0, 0, 0. This is 1, 1, 1, 1, 0. 1, 0, 0, 0, 0. 1, 1, 0, 0, 0. 1, 1, 1, 1. So we're going to count our rows. This is row 0, 1, 2, 3, and 4, right? And then I'm going to show you, we need a tuple, right? Because we want to count, we want to go through each row, save its index, and save the number of soldiers. Here there are 2, here there are 4, here there's 1, here there's 2, and then here there's 5, right? So this is the number of soldiers, and this is the row IDX, right? And we want to, so we want to get a tuple at each row containing these and replace them in a list. 2, 0, 4, 1, 1, 2, 2, 3, 5, 4, right? After that, we sort this list of tuples. Automatically, our question wanted us to sort first by the number of soldiers, and then if the soldiers are equal, the the row with the older index is considered weaker, so it comes before, right? So in any case, when you sort this, our weakest, right, in our result, our weakest will be this side, and as we ascend, our strongest will be this side, right? So when we sort this, our weakest is going to be 1, 2, right? It's going to be this one. Then it's going to be 2, 0, because 2 has an older index. Then it will be 2, 3, right? Notice these two have the same number of soldiers, but the indices are. We choose this one as the weaker one. Then it will be 4, 1. Then it will be 5, 4, right? But now they want us to return, not in this way, but in terms of the indices, right? The row indices, which are these guys, right? And so the row indices will be 2, 0, 3, 1, 4, right? And they want us to return the K first. In other words, the K weakest, right? So the way we're going to do it is we're going to iterate through each, summing them up, summing up the number of ones, which is basically the sum of the whole row. And then we'll be adding it to a list so that we have a list of tuples. And then we'll sort this list of tuples. And then we'll get this. And then we'll pick out after we've sorted it, right? We'll pick out each index. And then we'll return the kth. So now, one thing you should know, once you have, say, a list of tuples, let's say it's called result, and use .sort, it automatically sorts it by the index of the tuple at 0. This is how we access the tuple 0, 1, 0, 1, right? So it automatically sorts based off this, right? Or let me say this, right? But if you want, which isn't needed for this problem, so this is also means sort key is equal to lambda x, which is the tuple, x, which is the tuple x at index 0, right? If we had wanted to sort based off the indices, we would have written 1, because we're grabbing the tuple and we're choosing to sort by the second index in the tuple. So let's write this code out, right? Another thing you realize is instead of summing, we may decide to do binary search. But so now let's write it out. I'm spending too much time on the explanation. So we create our result array to place tuples of tuples containing 2 values. The number of soldiers per row with the row index, right? So we say for row in, so we create the result index, right? Then we iterate through row by row. So we say for row, let's call it for row idx, row in enumerate will return, for each row it will return its index, or it will start from 0 after every row and put it in row index, right? So matrix, right, the matrix. Then we sum up the row and add it to the result as a tuple with the row index, right? So result.append, we're going to use the sum function of the row and the row idx. So what we're doing is this step, right? We're going row by row, adding. To the left, we have the number of soldiers, and to the right, we'll have the row index, right? Okay. So after we're done with here, we sort our result list, which contains the tuples, right? And as we know, result.sort sorts the tuples based off the value at index 0 in the tuple, right? If we wanted something different, it would have been result.sort key is equal to lambda x at 1, right? So let me actually put this here. i.e. result.sort key is equal to lambda x into 0, right? Then now that our tuple is sorted, our list of tuples is sorted, we remove the number of soldiers and only keep the row index. How do we do this? We'll create a new one called final result, and then it will be for tuple val in first result, we get the value at index 1 where we kept our index, right? So we say final result dot append tuple val at index 1, right? Then since they want us to return the k weakest, i.e. k first values, we simply return final result up to k, since it's a zero-based index, right? So let's run this and see. Where did I make a mistake? Takes exactly, oh, it was supposed to be like that, sorry. I forgot the extra braces here, right? First result, final result. Oh, this was supposed to be final. Sorry about that. Where did I make the mistake? Final result. Oh, it was supposed to be in result. Sorry about that. Okay. So voila, this works. All right. So this is an O of m by n because we are going through the whole, when we are summing here, right? If the length of the row is, if the number of columns is n and the length is m, this is an O of mn right? It's upper bounded by O of mn. But then when we are sorting, sorting is going to be O of m log n. O of m log m, where m is the length of the row. But we can improve this time by doing it m log n, such that it's upper bounded by m log m, right? And how do we do it? Instead of using the sum function to sum this up, we create our own function which does it in log n, which does it in log n time, so that it will be m in terms of row, and for each time it will do it in log n instead of n time, right? So let's implement that function here, right? So we'll call it def sum binary. We'll call it sum binary, right? Let's call it binary sum. Binary sum. Okay, sum binary is fine. Sum binary. And what does it take? It takes a row. Let's call it row vals. So it takes a row, right? So the first thing we're going to do is since we're doing binary search, our I is equal to 0, our j is equal to length of row vals minus 1, right? Then we iterate through, right? So while I is less than or equal to j, what do? We calculate our mid, which will be I plus j divided by 2. We know some people may want it written as I plus, in brackets, j minus I divided by 2. So what do we do this? If row vals at mid is greater than or equal to 1, I is equal to mid plus 1. Why? We want, once this binary search has been exhausted, we want our I to be at this position, right? We want to exclude all of them such that our I is at this position, our j is at this position, right? And how this will, once we've done this, right, we simply iterate from this position up to here to add them up, or we can simply return I, because I, for example, let me erase all this so that you can see what I'm saying. So say we have our matrix, right? And we have 1 1 0 0, we have 1 1 1 0, 1 1 0 0, 1 0 0 0. If our I ends up at this location, it means we've excluded all the numbers greater than or equal to 1. This is index 0, 1, 2, 3. So we can iterate from this position up to here while summing them up and return that. So that means we've done it in log n time. Or we can simply return I, because I will be at the index that is equal to the sum of the rest of this. Or we can simply return j plus 1, because j will be at the last index and we can return j plus 1. So let's do it here, right? So this is, we are excluding all the ones to the left of I. Else, j is equal to mid minus 1. We are excluding all the zeros to the right of j, right? i.e. row vals at mid is greater than 0, right? No, is less than or equal to 0, right? So once we come here, this you could have written it as equals to 1s as well, because there's no value. We know there's no value greater than 1. So if it's equal to 1, you just extend it. So when we come here, we either sum up to just before I, or we return I, since it will be at index sum of the left of I, right? So return I or return j plus 1, right? So that is our sum binary function, and we can try it out here, right? We've replaced sum with sum binary. So let's run the code. Voila, it works as well, and it's a bit faster. So this means our solution is upper bounded by, instead of being upper bounded by m times n, which is m by n rows, it's upper bounded by m log m, which is what we used to sort here. But when we are doing this, it is m by log n, n being the length of the row. So that is the solution, and thank you, bye.